In this video, we're going to be taking a look at kinematic curves, and we're going to take a look at all the different concepts and shapes of every kind of motion graph that is constant velocity and uniform accelerated motion. So for the first half of the video, we're going to concentrate on position versus time graphs, velocity versus time graph, and acceleration versus time graphs. We're going to talk about every different type of shape, direction, and location of graph, discussing what all of the different shapes and locations mean. After a full breakdown of all of these three types of graphs, you're going to be able to kind of do a little bit of practice and test yourself. We're going to have 3 examples where you can go ahead and give them a try and try to test out your new skills. And then from there, we're going to have a full explanation of how to do those 3 graphs as well. So let's go ahead and get into an explanation of how all these curves work. In physics, when studying kinematics, you may get a word description or a word problem where you have to translate that into a graph, or you may get a certain graph, such as a velocity versus time graph, that you have to translate into a position versus time graph, or an acceleration versus time graph. So there's a lot of different combinations of things that you may have to do, but to understand every kinematic graph, you want to understand what each of the shapes, directions, and locations mean and what they represent as far as the motion goes. So we're going to take a look at each of these types of graphs, and we're going to talk about how all of those things relate to the meaning of the actual motion itself. So when we take a look at the shape, we're going to take a look if it's straight, curved, flat. As far as the direction goes, whether it's upward or downwards, flat, or in some cases towards or away from the x-axis, and then also the location as well. Where is your line? Is it above or below the x-axis? So let's start with our position versus time graph. Our position versus time graph is telling us the position at any given point in time of the object or thing that's in motion. If anything is rising on the graph, that just means that it's moving in the positive direction. If anything is becoming lower on the graph, that means it's just moving in the negative direction, but that doesn't tell us anything about how fast or slow they're going. Now let's take a look at the different types of shapes that you might see. If you see a flat curve or a flat line on your graph, that means that the object is not moving at all. It's at rest. So if the line is flat anywhere along the graph, that still means the position stays constant, which means the object isn't moving at all. Now, if the object is moving, but the line is straight, that means you would have an object that's moving at a constant velocity. Because remember, the slope on a position versus time graph tells you what the velocity is. So in any graph, the slope is telling you about the rate of change, and this is the rate that the position changes per time, which is the velocity. And then this is a constant slope, which means that it's moving at a constant velocity. And again, the only difference between these 2 blue lines is just the direction, because anything that's rising on the graph is moving in the positive direction, and anything that's becoming lower on the graph just means it's going in the opposite direction. Now, the last type of shape that you will typically see in a position versus time graph is something that is curved. So the word curve doesn't necessarily mean the shape of it is curved. A curve is just referring to any line that's on a graph, whether it's straight or flat. So now we're actually talking about shapes that are actually curved on the graph. So there are various types of curves you'll see, but for the most part, there's pretty much only 2, and they look something like this. So we have a few different types of curves here. Let's pay attention to the purple one first. So the purple one is doing the same sort of thing, whether it's rising or falling. And what you want to take a look at is if you're looking at accelerated motion, you're for sure going to have a curved line. And we know this because if the slope is changing, it's going to create some kind of curve. And if the slope is changing, that means the velocity is changing, which means the object is accelerating. So if it's flattening out, that means the slope is becoming progressively closer to this one, which is at rest. So it's heading towards zero, which means the value of the slope is decreasing, which means that the object is slowing down. So this one is slowing down in the negative direction, and this one is slowing down in the positive direction. And our final one is the one in orange. That's one that becomes progressively steeper. The steeper the slope, the greater the rate of change, which means that its velocity is becoming greater and greater, which means the object is speeding up. So this one is speeding up in the positive direction, and this one is speeding up in the negative direction. So depending on your scenario, you have to think about what the slope is supposed to look like. Is it supposed to be straight? Is it supposed to be curved? In which direction it's heading? Now let's move over to our velocity versus time graph. So the rules for the velocity versus time graph are very different than the position versus time graph because it's telling you how fast it's moving at any given time. So this is just telling you the position. This is just spotting how far you're at from the origin. This is telling you how fast you're going. So it's going to be very different as far as the rules go. So for our second graph, to recognize whether it's going in the positive or negative direction, you just take a look at whether it's above the x-axis or below the x-axis. So anything below, which means a negative velocity, that would represent any type of line on here that's becoming progressively lower. And then for anything that's above here means it's a positive velocity. That means anything on here that's rising up on the graph. Now, we're going to use some terms that are going to be a little bit different for our velocity versus time graph. So any line that's flat is going to be moving at a constant velocity. So it could be something that looks like this, like this, or something that's right on the actual x-axis itself. So all of them are moving at a constant velocity. This is a constant positive velocity. This is a constant negative velocity. And a constant velocity of 0 would mean it's at rest. So the only point where you can possibly represent something at rest is right on the actual x-axis itself. All right, now if we're taking a look at something that's accelerating, remember something that's accelerating means that its velocity is changing. So we are trying to distinguish between whether it's speeding up or slowing down. On the position versus time graph, to distinguish between those two, we took a look at whether it was flattening out or getting steeper. Now for the velocity versus time graph, it's going to be a little bit more simple. We just want to know if the number is getting greater or smaller. But remember, negative in physics just means in the other direction. So something that has a greater negative number is actually moving faster, but just in the other direction. So in order to identify something that's going faster would just be something that is moving away from the x-axis. And then for slowing down again, we want something that has a decreasing velocity. So it could start over here, and then it's going to work its way towards the x-axis. Okay, now this can be a little confusing because a lot of times when people think of, speeding up, they hear the word up, they look for something that's literally moving upwards, and if for slowing down, they're literally looking for something that's moving downwards. Okay, so something can be speeding up and it could be a positive slope or a negative slope. as long as it's moving away from 0, this is getting progressively faster in the positive direction. And for this orange line over here, it's getting progressively faster in the negative direction. Same thing with slowing down. You can have a positive slope or a negative slope. So if you take a look at the purple line here, the one that's slowing down, if it's heading towards 0, that means it's getting closer and closer to becoming at rest. So again, you don't take a look at the actual slope, whether it's a positive or negative slope. You just take a look at if it's moving towards or away from the x-axis or towards away from 0 meters per second. So this one is starting out at a fast negative velocity and getting progressively slower and moving towards 0. And this one is starting at a high positive velocity and decreasing, and again, also heading towards 0. Now moving to our very last one, the acceleration versus time graph tends to be the least complicated because when studying high school physics, you typically don't get into too much change in acceleration. We're mostly just taking a look at constant acceleration. So for an acceleration versus time graph, it just tells you how fast the acceleration is changing per time. So from our velocity versus time graphs, the slopes tell you the acceleration from this graph. So we saw that how fast the position changes per time represents the velocity, and how fast the velocity changes per time represents the acceleration. So for our very last one, there's not too much going on here. We have a line basically above 0, on 0, or below 0. So for our acceleration versus time graph, this one doesn't get very complicated as far as shapes go. So typically, if you're just translating a velocity versus time graph to an acceleration versus time graph, you just simply have to take a look at the slope. On this graph here, we have no changing slopes. They're all constant slopes. We only have changing slopes over here where it's curved. So if we were to translate this orange line right here into the acceleration versus time graph, this is a constant positive slope, so that's a constant positive acceleration. Okay, just like this purple line over here, it's a constant positive slope, so constant positive acceleration. Okay, and this positive acceleration could technically mean speeding up or slowing down. If something is already positive and you're adding a positive number to it, then it's going to get progressively larger in the positive direction. If something is negative and you add a positive number to it, it's going to decrease that negative number and make it head towards 0. So basically the rule is, if you just take a look at the slope for the velocity versus time graph, that will be represented on your acceleration versus time graph without too much in-depth thinking from there. For example, if you have any sort of flat line that is a 0 slope, that means a constant velocity, therefore there's no acceleration. Every single type of constant velocity curve is going to be represented right on the x-axis over here. And then for negative acceleration, it works similarly to the positive acceleration, as in if there's anything with a constant negative slope, such as this purple line here or this orange line here, it's going to be represented by a straight line and a flat line underneath the x-axis on the acceleration versus time graph. So those were a lot of rules, a lot of different shapes, a lot of different things to look at for each of these graphs. So when translating from one graph to another, those are just a lot of different things to consider and think about, whether you're reading a word problem or translating one graph to another. These are a bunch of different ideas that you can use to help you interpret the information and then hopefully accurately develop the graph that you need. Now we have 3 examples of some kinematic curves. We have a position versus time graph in green, a velocity versus time graph in orange, and an acceleration versus time graph in red. And we're going to be working horizontally to translate the green graph into the velocity graph and then into the acceleration graph. Same thing with the orange one. We're going to translate it out to the position graph and then to the acceleration. And then for the acceleration graph, we're going to translate it into the velocity and position. So you can go ahead and pause the video and give these 3 practice problems a try. And then after you've completed them, you can go ahead and press play and listen to a full explanation of how to translate these 3 graphs. So for each one of these, I made them a 3-part graph so that we could do 3 different types of motion within one problem. So let's call this section 1, section 2, and section 3. So here are details that I'm going to want to be paying attention to. For section 1, it's slanting backwards in the negative direction. So we have a negative velocity. And because my line is straight, it has a constant slope, which means it has a constant velocity because the rate of change on a position versus time graph is the slope, and the rate of change of a position time graph is the velocity. So if it is a constant negative slope, then we have a constant negative velocity. Then for number 2, again, we're analyzing the slope, but if the position is staying constant, that means that we're not moving and the slope is 0. So we're exactly on the x-axis here on our velocity time graph to show that the object is at rest. Now for number 3, if you notice something is curved, that means that the slope is changing. If the slope is changing, that the rate that it's moving is changing, which means it's accelerating. The second thing you want to identify is if the curved line is getting steeper or more flat. So is it becoming more vertical or more flat? So this one is clearly becoming more vertical. So it's rising up, which means it's going in the positive direction, and it's becoming progressively more steep. So that means positive and getting progressively more steep, which means that it is increasing its positive velocity. So then this would be your section 1, 2, and 3. A straight constant negative slope for a constant negative velocity, no slope, no change in position, so the velocity is 0. And then we have an increasing positive velocity, so we have an increasing positive slant upwards on our position versus time graph. Now, every time you go from a velocity versus time graph to an acceleration versus time graph, that one is typically a little bit easier because, again, you just look at the slope, but there's not a whole lot to look at with these slopes because this is completely flat and this is completely flat. So section 1 and 2 have no acceleration at all. Now that might seem confusing because these are very different. One is completely motionless, which is section 2, and then there's one part that's moving. But within each section, there's no change in velocity. This is a constant negative velocity that the way that the person or thing is moving backwards stays constant, and then the way this thing moves, which is not at all, stays constant. So we have no acceleration for the first 2 sections, and then because there's a constant positive slope here, there is a constant positive acceleration for section 3. So when going from position to velocities to accelerations, you analyze the slope of the position versus time graph to get the velocity versus time graph, and then you analyze the slopes of the velocity versus time graphs to get to your acceleration versus time graphs. Now we're going to use all of those same ideas and apply the same concepts and skills to our second problem over here. So let's go from the velocity versus time graph to acceleration. So it looks like we have a constant negative slope all through the first 2 sections. Again, we'll call that section 1, 2, and 3. So if it's a constant negative slope, then we have a constant negative acceleration for sections 1 and 2. And then at the very end, we have no change in velocity, which means that we have 0 acceleration because the slope is 0. All right, now working backwards, this can be a little bit trickier. So what you want to do is either jot down some little notes or just kind of go through all of these ideas in your head. So here are the things that I go through. Number 1, this velocity is positive. It's positive because it's above the x-axis. Okay? And because the line is moving towards 0, that means it's slowing down. So something positive and slowing down means that it should be rising on the position time graph, but because it's slowing down, the slope should not get steeper. It should be becoming progressively more flat. So I'm going to rise up and become progressively more flat to show that it's slowing down. That's section 1. Okay, for number 2, this is a little tricky because this line is all continuous, so it seems like it's continuing the same type of motion, but now it's going from a positive velocity to a negative because it's dropping down below the x-axis. Okay, what that means is if I have negative velocities, that means I should be going lower and lower on my position versus time graph. Now, this isn't slowing down in the second position or the second section either, because you find out if things are going faster or slower based on whether they're moving towards the x-axis or away from it. So this one is moving from a positive number towards 0, and this is moving from 0 to, we'll say, -1, -2, -3, -4. So it's increasing its negative velocity. So I want to go down on the graph, and then I also want to get steeper and steeper and steeper. Okay, so it's going to look something like that. Okay, and then for section 3, I have a constant negative velocity. So whatever velocity I ended off with 2, I'm going to continue with that constant negative motion, and I'll actually end up sort of dropping off below this graph, but I'll sort of continue it on and then have a constant negative slope to show this constant negative velocity. So moving from this step to this step was definitely one of the more tricky ones. Okay, now for the last one, this is actually a very uncommon type of problem, but I'll just tell you the concepts and ideas that you would use to approach this type of problem. Now, the reason why this kind of problem isn't given very much is because this acceleration versus time graph is the least descriptive one as far as telling you which direction you're going and if you're speeding up or slowing down. Now, if you remember, we took a look at the slope on the velocity versus time graph to go over here to show that we had a constant negative acceleration. Now, this is a constant positive acceleration, which just means we have a constant positive slope. So that positive slope could look something like this. Okay, it could look something like this. It could look something like this. Those are all constant positive slopes, but they're different types of motion. This one's positive, this one goes negative and then positive, this one's all negative. Okay, that's why I said it's not very descriptive. So I'm just going to go with the original one and get rid of these previous two, and I'll show a constant positive slope for a constant positive acceleration. And then for this part, it is a constant negative acceleration, so constant negative slope, and then something with no slope at all. Okay, and then again, we'll call this section 1, 2, and 3, 1, 2, and 3. Okay, now this is the correct shape no matter which way you look at it, except this entire graph could be shifted upwards or shifted downwards. Now, going off the one that I drew, if I have a increasing positive velocity, then I'm going to want to rise up on the graph, and to show the increasing rate of movement, I'm going to make the slope steeper and steeper. So that's going to be section number 1. And then I'm not going backwards now, but I'm decreasing my positive velocity towards 0. So I'm going to rise up, but the slope is going to become more and more flat because the rate that it's moving upwards is getting smaller and smaller than actually hitting 0. When it hits 0 completely, then that means you're remaining at exactly the same position because you are at rest. Okay, so with those 3 different examples, I hope that's helpful to you in analyzing different graphs and being able to create graphs starting with position, velocity, or acceleration. Thank you very much for watching and listening.